Okay, so in chapter 9, as you'll no doubt recall, we've been talking about aldehydes and ketones, which are a pretty important class of functional groups. And I think it's good to mention them in the same chapter, as they have very similar reactivity, maybe not absolutely identical, but pretty darn similar. Certainly much more similar to each other than to any other functional groups. And we went over the formation of the hydrate from an aldehyde or ketone by adding water in either alkaline or acidic medium. We pointed out that not only is this reaction not synthetically useful, if anything, it's the exact opposite. And it's normally something that we try to prevent from happening by storing our aldehydes and ketones over some drying agent. But the reaction is illustrative in terms of the mechanism, and I think it's good for you guys to be exposed at least a little bit to how mechanisms differ from one another if they can happen in either acidic or alkaline medium. And that certainly is an example of a reaction that can go either way, can be in either acidic medium or alkaline medium. And I don't normally want to really emphasize mechanism very, very heavily, but I don't mind doing it in that case or in the case of our next reaction when we talk about cyanohydrins, because these reactions are short and relatively simple in terms of their mechanism. Once we get to hemiacetals and acetals, then you won't be responsible for the mechanism. It's known. It's just rather lengthy, and it's not that I don't think you can. It's not that I don't think you can handle it. I think you can. But as with so many things, first of all, we have limited time, and second of all, I can't come up with any conceivable educational benefit for me to force you guys to learn those mechanisms. Therefore, I won't. And then we'll end off with a discussion of reduction of aldehydes and ketones. And a good place to make the connection there is we've already talked about the oxidation of alcohols, secondary alcohols and primary alcohols, respectively, to ketones and aldehydes. That we've already discussed. So this is essentially the opposite of that. We have reducing agents that will go in the opposite direction, from a ketone to a secondary alcohol, or from an aldehyde to a primary alcohol. And we'll cover those. And that, I think, will leave us in a good place to start with carbohydrates on Wednesday. That will be really, in my opinion, possibly the most involved of our biochem chapters in terms of the things we'll need to say about structure and reactivity. But we'll be ready to do that because carbohydrates turn out to be nothing other than polyhydroxy aldehydes and ketones, meaning aldehydes and ketones with a whole lot of OH groups plastered all over the molecule. And we will have just completed the chapter in aldehydes and ketones, and we've already completed the chapter on alcohols. So we'll be in good shape, I think. And yeah, and so I think that's all I need to say about that. Good. So anyway, speaking very much in general terms, what is a cyanohydrin? I would say a cyanohydrin is the product that you'll get by starting with any aldehyde or ketone, and this is very general. You can use any aldehyde or any ketone, so R1 and R2 can be pretty much whatever you want. And the way your book introduces it, and they're not wrong, is that we treat that aldehyde or ketone with aqueous hydrogen cyanide in the presence of a catalytic amount of base. So you just need a little speck of base. And you wind up adding the equivalent of HCN across that carbon-oxygen pi bond. And I think you can see what we get as a result. The carbon-oxygen double bond becomes C single bond OH, and that fourth bond to that now sp3 hybridized carbon goes to a cyano group. By the way, little aside, please don't forget the structure of the cyano group, or you can even draw the structure of HCN. Please remember there's a triple bond there. So HCN has that Lewis structure. And the cyanide ion, Cn minus, is just this without the proton. But please note the minus charge in the cyanide ion is on the carbon, not on the nitrogen. Both have a lone pair on them, but if you work it out, it's the carbon that has a formal charge of -1. So and you can write Cn minus, it's fine, but please do be aware that's the structure of the cyanide ion. It is a triple bond in it. And that type of functional group is called a nitrile functional group. Maybe not one that we stressed a great deal when we learned our functional groups. In fact, I simply don't remember, it's so long ago. We might not even have mentioned the nitrile functional group. But it has some limited usefulness. It's not something you run into all the time. I'll explain at least one way in which we can use this when we complete our discussion of cyanohydrins. But this is the setup that your book talks about: aqueous HCN with a catalytic amount of hydroxide ion. Alternately, you don't have to use HCN. You can also use a cyanide salt, like sodium or potassium cyanide. And in fact, if you dissolve sodium cyanide or potassium cyanide in water, you're going to get a little bit of hydroxide ion anyway. That just comes out for free, because the cyanide ion is a moderate base. And I would say the opposite also. HCN, it's a moderate acid. It's certainly not terribly strong, also not the weakest acid in the world. Likewise, the cyanide ion, which again, remember, when we write NaCN, what we mean is Na plus Cn minus, right? The charges are still there, we just don't write them. Same thing with KCN. So the charges are still there, we just don't write them when we write the formula of the compound. So these are both simply Cn minus. They're both just the cyanide ion. The sodium and potassium ions don't play any role in the reaction. They're spectator ions. And either way will work fine. Same result. You'll wind up getting the cyanohydrin. If in real life I wanted to make a cyanohydrin, I would never by any means use HCN. Hydrogen cyanide gas is exceedingly dangerous. One good whiff and you've had it. Very, very toxic. Of course, sodium and potassium cyanide are plenty toxic too. The difference being you'd have to very purposely ingest it, or someone could get poisoned, like in one of those spy novels. But there's time. The time is ticking, but you do at least have time to get to the hospital and get the antidote with these salts. With HCN, not so much. I've luckily not had the pleasure, but I've heard of labs where they were using dangerous materials that would liberate HCN very carefully in the fume hood, and they would have the syringe like right there on the wall. So in case anyone got exposed, someone would run up and give them the shot of the antidote. So very, very scary. Lucky, I don't think I've ever used trimethylsilyl-cyanide. I hope not. There are things out there that will liberate HCN. Sodium and potassium cyanide I've used, and you treat them with respect, but as long as you don't do anything crazy, and or acidify it, and as long as you're careful, it's fine. Good. So I think that's all I need to say about that. But let's see, where was I then? So the product is of this type. We call compounds like that cyanohydrins. And they're of some usefulness themselves also. But just to give an example so that we can go over the mechanism, let's make R1, let's go back to our friend acetophenone. So we'll say one of the R groups is a benzene ring, phenyl group, and the other one is a methyl group. So we could pick any aldehyde or ketone. And let's then stipulate that we treat this with HCN and aqueous solution. And just a little bit of base. Let's say we dropped in a few small specks of sodium or potassium hydroxide. What that's going to do is give us a little bit of the cyanide ion. That will deprotonate the HCN, which again is not the strongest acid in the world, but when put up against hydroxide ion, it's more than strong enough. Hydroxide ion will easily deprotonate a little bit of the HCN and give us some of the cyanide ion. The mechanism, though, would be the same if we used sodium or potassium cyanide. And again, the only reason I'm going over this mechanism is it's a very quick one. This one's just 2 steps. It's very analogous, in fact, to the reaction of an aldehyde or ketone with aqueous base in order to give the hydrate. It's very, very similar. The only difference is that the nucleophile that attacks the carbonyl, as we've been teaching ourselves to get used to expecting that to happen, instead of the nucleophile being hydroxide, it's cyanide. Other than that, it's identical. If you know one, you know the other. Once again, we will break our carbon-oxygen pi bond and put the electrons in that bond onto the oxygen nucleus, and you'll get an intermediate with a minus charge. And then C triple bond N. I can't help myself. I'm going to draw the cyano group like this. I feel like I really have to, because again, that carbon here in the middle, the cyanide carbon, is sp hybridized, so it's linear, right? But you have a minus charge here on that oxygen, and that can then pick up a proton from a water molecule, just like we had the last time. Or frankly, and I say this in the class notes, if instead one were to put here an HCN molecule rather than a water molecule and use that as the acid, I have no problem. I'm sure both of those actually happen. Whichever the case, the end result is going to be the cyanohydrin. And so, like I said, the reason that I'm bothering with the mechanism is this is another one where the mechanism, the curved arrows, is relatively simple. In this case, it's just 2 steps. And not only that, I think it's illustrative to go back and compare this to, I'm just going to go CN now because I'm lazy, but there's your cyano group or your nitrile group. But again, if you compare this to treating an aldehyde or ketone with H2O and OH minus to give the aldehyde or ketone hydrate, I'm hoping you'll be able to convince yourself it's essentially the same mechanism. The only difference is that instead of the cyanide ion attacking the carbon, you have OH minus attacking. And I'm always a big fan of it when you can learn 2 things at the same time. And this is one of those cases that we do that. So that's why I'm taking the trouble to teach the mechanism here. I think this is the last mechanism we'll have in this chapter. I certainly am not going to go there with hemiacetals and acetals, but I think it's illustrative in this case, which only begs the question, so you've got your cyanohydrin, well, so what? And I'll at least spend a little bit of time on that topic. Any questions before we do that? Well, so again, I would suggest you make up your own aldehydes and ketones. Get with a classmate, friend, boyfriend, girlfriend, worst friend, brother, sister, uncle, aunt, father, mother, cat, dog, and have them make up some aldehydes and ketones for you. Let me know if you have any luck with your cat. I've been working on Bella the cat for years, and she just is not developing any kind of aptitude for that type of thing. Okay, so, but that's the best thing you could do, and then work out the mechanism and figure out what the product looks like. And of course, I happen to go in clockwise order here, phenyl, OH, methyl, C, and it doesn't matter. Not when we're drawing just flat structures like this, when we're not concerned about stereochemistry. Indeed, that carbon is chiral now that I think about it, at least in this particular case. But you would get both R and S. You would get a racemic mixture. And normally, watch OWL carefully, but I think, and in a case like this, I think you'll find OWL will say, don't even worry about stereochemistry. And so as long as that's the case, it doesn't matter which order you draw those 4 groups in. It's the same thing. Good. So that being said, let's clear all that. So let's say that you have the cyanohydrin. What can you do with that? Well, it's actually not very far from a cyanohydrin to an amino acid. What do we put here? CN. So there are, in fact, ways to wind up with an NH2 group up here instead of OH. And actually, all you need to make that happen, remember, our reagents before were HCN and water. All you needed instead is to make it HCN and ammonia, liquid ammonia, NH3. So you have to cool it down quite a bit to get liquid ammonia, as I think we might have discussed earlier. It's all kind of a blur. But in any case, And as it turns out, that will give you NH2 instead of OH. And this is one of the best ways to make an amino acid in the lab. So let's just say, and again, I don't really care that you memorize reagents for it, but we certainly have ways that we can get NH2 over here instead of an alcohol functional group. So you can just take my word for it. There are ways of doing that. And once you have this kind of amino nitrile type of thing, we're going to learn in chapter 10. I'm just going to put 10 here in parentheses. We're going to learn that you can hydrolyze this nitrile and convert it into a carboxylic acid. So you're not responsible for this reaction yet. We'll get there. But that's known as a hydrolysis reaction. And as it turns out, this amino group is going to wind up protonated. So you'll get NH3+. And instead of CO2H down here, you'll get CO2-. This now is something we'll discuss in the chapter on proteins and amino acids and polypeptides. This funny form here where you have both the plus charge and a minus charge, you might have talked about species like that a little bit in Gen Chem. They're called Zwitter Ions. ZWITTERION. And the definition of a Zwitter ion is, as you see here, it's something that has both a plus charge and a minus charge in the same molecule. And once again, I can't believe it's happening twice in the same semester, but if you're one of the 11 people who, like me, took German in high school, you once again have won the internet. The German word Zwitter means twin. So it's a twin ion. You got both a plus charge and a minus charge in the same molecule. Or actually, it's not impossible. You might even have spoken some German at home. So you'll know that word. Point being that if you can get your hands on a cyanohydrin, or maybe alter the reaction a little bit so you get an amino group instead of an OH group, then you're just one step away from making an amino acid. And in fact, this particular one, well, this particular one you wouldn't actually get. This particular one would not be a naturally occurring amino acid. If the phenyl group were a hydrogen, then you would have alanine. And you would actually have both D and L alanine. You'd get both of them. You'd get a racemic mixture. So you'd need to separate them. That's a whole other story, and we'll talk more about that in chapter 17, I think, is our chapter on amino acids and polypeptides. But I just wanted to show you this now so that you're ready for that when we get there. Yes, I'm sorry, I forgot to put a heading. My heading over this is going to be conversion of a hemiacetal to an amino acid. Sorry about that. I'm trying to learn to always put headings. Oh, this one here, that's a hydrolysis reaction, and we'll get there in chapter 10. We'll learn that word in chapter 10, and I'll define it fully, and we'll take care of that when we get to chapter 10. But this is conversion of a cyanohydrin to an amino acid. And yes, this whole thing, all of this that you see here is conversion of a cyanohydrin to an amino acid. And this last step is a hydrolysis step. Hydrolysis comes from two, I think, Greek terms meaning loosening by water. And that's exactly what we do. By the way, the nitrogen in the nitrile winds up in a molecule of ammonia. So it doesn't just disappear or turn into an oxygen. We're not doing nuclear chemistry here. But the major organic product is actually going to be a substituted amino acid. And so, you know, making some changes to how this is done, you can actually come up with, you know, amino acids of the type that you'd find in living systems. So this was all just to point out that there are other things you can do with cyanohydrins as well. This is one of them. So they're not a completely useless compound. Good. So I think with that, so much for cyanohydrins. Any other questions on that? So again, don't simply memorize what we did above. Be sure that you're ready to consider what would happen if you treated any aldehyde or ketone with HCN, including one you've never seen before. So Al will give you some ideas as to what that might look like. But don't just memorize the examples we do in class. Good, so I think with that, we're ready to get to hemiacetals and acetals. And like I said, with that, we're also done with mechanisms in this chapter. That's enough. I don't mind having done these few because they're relatively short and relatively simple. But from here, the mechanisms are known, but they're very steppy. So rather than writing hemiacetals and acetals here for the heading, I'd rather put the words below the structures that they're definitions for. So in general, let's start once again with a generalized aldehyde or ketone. This could be any aldehyde or any ketone. So R1 and R2 can be whatever you like. And what we're going to do, instead of treating this with aqueous acid, H3O+, we're going to use an alcohol. Let's call it R3OH. With an acid catalyst. So just a few drops of sulfuric acid or phosphoric acid or whatever you happen to have in the cupboard, so to speak. And I'm using square brackets here to show that you get an intermediate, a particular type of intermediate known as a hemiacetal. And I'm going to write that down in just a second. Just let me draw the structure first. It looks very much like the hydrate of the aldehyde or ketone, except that instead of two OH groups, you have one OH group and one alkoxy group. So again, the square brackets just mean that this is an intermediate, and this type of compound we call a hemiacetal. And these are sometimes useful in their own right. So the definition of a hemiacetal is what you see here. It's an sp3 hybridized carbon attached to an OH and an alkoxy group. So that's the definition of an acetal. I'm using a picture to make the definition here. Now, with excess alcohol around, the alcohol here is our solvent, so there's as much of it as we need. This is eventually going to lose a molecule of water and make a full acetal, with two of these OR3 groups on it. So this is now what we mean by an acetal. So the definition of an acetal is what you see here. It's an sp3 hybridized carbon with two alkoxy groups attached. And you will also, of course, get a molecule of water, which that'll be an inorganic side product. That's the fate of this OH group up here. That winds up in a molecule of water. And so in the end, you have the alcohol molecule actually adding twice with loss of a water molecule, and this type of compound that you get at the end is known as an acetal. And again, the full mechanism is known, but you won't be responsible for it. Although I will say, if you're curious, getting to that hemiacetal is just like the previous two mechanisms we've learned. In particular, this looks just like making the hydrate with H3O+, except instead of water as the solvent, the alcohol is the solvent. So up to here is very clear. Getting from the hemiacetal to the acetal is a bit more involved, and so you won't be responsible for that. But just so you know, the mechanism is known. It's just, I don't want to burden you with it. So what you need to know is that if you start with any aldehyde or ketone, whether it's one you've seen before or not, and you treat it with an alcohol and an acid catalyst, generally these require heat as well. They tend to be on the endothermic side. then the structure that you will get as a result, and I believe I've given you yeah, I mean, I've laid this out for you in the class notes, but I'll just say what you need to do in order to get the right structure is you change C double bond O to C single bond O, and then you put on whatever the alkyl group is on the alcohol. If this is methanol, then you make it OCH3. If it's ethanol, OCH2CH3, just whatever the group is in the alcohol. And then you'll need a fourth bond to carbon, so you just put another of that same alkoxy group on. Though there's a couple of variations on this, which are pretty important, but we'll get there. Yeah, we'll get there next. There's plenty of time. So we'll do some examples of this next. But that's basically how you get the structure of the product. For example, let's say that we started with cyclohexanone, which has a structure just as you would guess. Cyclohexane with a ketone on it. So there's your cyclohexanone, and this is the example I put in the class notes also. Let's say if cyclohexanone is dissolved in methanol in the presence of an acid catalyst. So here's methanol, CH3OH, and maybe just a speck of sulfuric acid or something. So, and it might also say here H2SO4 or some other strong acid. But whether they specify the acid or not, the result is the same. That's just a catalyst. And so I would expect that we would get out of it at first the hemiacetal, which will have OH and OCH3 up here. But eventually, and you'll know by the wording of the question whether you have to show the hemiacetal or not. At least the questions on OWL that I've seen are very clear. They want you to draw the hemiacetal or they want you to draw the full acetal product. And if we were to draw the acetal product, it would look something like this. There you go. So you see we have two of those alkoxy groups attached to that carbon. So that's the product, that's the organic product that I'd expect you'd get. And yes, you will get a molecule of water also. The phrasing of the question will make it clear whether you need to show that or not. OWL sometimes likes to make you guys show weird things like that. I think it's much more important to be concerned with the major organic product. So again, this, when you treat it with acidic methanol, you will at first get the hemiacetal, which looks just like the acetal, except you replace one of these OCH3s with OH. So just like you see up here, you have one OH group and one alkoxy group. So you'll have one OCH3 and one OH. And then that will keep reacting, and you'll replace the other OH group with another alkoxy group. You just look at whatever the alkyl group is in the alcohol, and that's what you put here. This is CH3OH, so you put OCH3, because that's what's in the alcohol. And so that's the final product. And that's going to be true in general, regardless of the ketone or aldehyde, regardless of what alcohol you use. So again, be prepared for this to be any aldehyde or ketone, even one you've never seen before, and for this to be any alcohol, which gets us to two important variations on this, one of which is going to be relevant to the chapter in carbohydrates, which we're going to go to next. Actually, in certain ways, both of which will be. Good. Any questions on formation of acetals and of the hemiacetal intermediate? What is the name of final product? It's the acetal of cyclohexanone with methanol. It doesn't have a special name. At least none that I can come up with. Do you mean this one here? You could say the dimethyl acetal of cyclohexanone, but it doesn't have a special name. Good. Other questions then? Well, just want to make sure I am recording. Good. Couple of interesting variations of this, or on this. I'm talking about cyclic hemiacetals in the class notes. And the compound I said to start with was 5-hydroxypentanal. So that name's in the class notes. 2, 1. So that's the compound that I referred to in the class notes, 5-hydroxypentanal. 1, 2, 3, 4, 5. And so what can happen is the OH group here can act like the OH group on methanol. And this is especially the case when you can form a 5 or 6 membered ring. I think here we're going to get a 6 membered ring. So I'll call the oxygen atom number 6, 1, 2, 3, 4, 5, 6. We're going to get a 6 membered ring from this oxygen attacking that aldehyde carbon. And so you won't get a full acetal in this case, but you will still get a hemiacetal. So this just needs an acid catalyst. Since basically the alcohol is contained in the aldehyde or ketone molecule, you've got the alcohol in there already, and so all you need is an acid catalyst. And I think you'll find that you'll get a 6-membered ring out of this. Let me put the numbers on the carbon so that you see what went where. Carbon 1 is going to be over here. That used to be the aldehyde carbon. Well, that looks like a double bond, though. Let me put it over here. That's better. 2, 3, 4, and 5 are all CH2s. And this is oxygen 6 that had been in the OH group. So that's the kind of structure you'd get. And sugars do this all the time. You can get 5 or 6 membered rings that way. I would say 3 and 4 membered rings, not so much. 7 membered rings and higher, not so much. But 5 and 6 membered rings are special. Those will pretty easily form a cyclic hemiacetal. And, can't spell today, cyclic hemiacetal. And that's very, very common with hydroxy substituted aldehydes and ketones. Again, as long as you can close a 5 or 6 membered ring, those are very favorable to form, right? Because we learned those are the ones that are not strained, especially 6 membered rings. It's very much like cyclohexane. You just replaced one of the CH2s with an oxygen. Other than that, it's very similar. And by the way, add a bunch more OHs on here, and welcome to glucose or galactose or one of these other ones. That's what those structures are like. So they're just, you know, a more substituted version of this. You'll see that when we get to chapter 16, I think. Well, why should I be guessing? Chapter 16. There it is. Yep. I'm going to get to chapter 16, which is on carbohydrates. So that's one variation on the whole thing that I think will be helpful looking forward to chapter 16 when we talk about carbohydrates, because they go from this open chain form to a cyclic form very readily. And so there's equilibria between all of these different things in an aqueous solution. So I'm only mentioning this to get us ready for that possibility. We'll talk about that more in chapter 16, but it's kind of relevant here. Another variation on this is what if your alcohol, instead of an alcohol, what if you have a diol, something with 2 OH groups? So for this, I'm going to go back to our acetophenone, since it's been around for a while. So what if we thought of something with 2 OH groups such that they both formed bonds to this carbon in such a way as to give us a ring, preferably a 5 or 6 membered ring? Indeed, that can be done very readily. But this is just another acetal that we're going to form. It's not a different reaction. It's the same reaction. Simplest one I can come up with is ethylene glycol. which is nothing more than HOCH2CH2OH. So it's a 2-carbon diol with each of the 2 carbons having an OH on it. That, by the way, is in your antifreeze. It's a liquid over a very, very wide temperature range. And so it can keep everything in the liquid state, whether it's pretty darn hot or pretty darn cold. So it's also hypotoxic. You don't want to drink that stuff. Okay, so let's say we use that as our solvent and added an acid catalyst. Well, if you consider what our hemiacetal is going to look like, this will still go through a hemiacetal. But if you think about it, CH2CH2, and what else do we have? We've got OH, and we've got CH3. So that's what our hemiacetal will look like. But now, instead of a second molecule of the alcohol coming in, we've got another OH group right here. And actually, this reaction is way easier to accomplish than if we needed a second alcohol molecule to come in. Far easier if the reaction can be done intramolecularly, as long as you're forming a 5 or 6-membered ring. And in this case, I hope to convince you that we'll get a 5-membered ring. I'm just going to arbitrarily number these atoms. 1, 2, 3, 4, 5. So we'll get a 5-membered ring. This oxygen is going to form another bond to that carbon. This is the OH will wind up losing in a molecule of water. You will again get a molecule of water. And our full acetal will include a 5-membered ring. So that's another variation on this to be aware of. It's not a different reaction. It's the same thing. It's just that you wind up with an acetal that just happens to be cyclic. And so you get something that looks like this. Doesn't have a special name. It's just an acetal that happens to be cyclic. Let me just make that bond look a little better. There we go, something like that. And if instead of ethylene glycol, we'd used 1,3-propane diol, so 3 carbons with OHs and carbons 1 and 3, well, you'd get the same type of thing, but with a 6-membered ring. And that would also be fine. That would also form very readily. So as long as you're forming a 5 or 6-membered ring, you're good to go with this type of cyclic acetal. I'll even put here a cyclic acetal. But this is not a different reaction. It's the same reaction, just a variation on it. So cyclic hemiacetals are a thing, cyclic acetals are a thing. And that's, I think, really all we need to say about that. Good. With that, I think we're done with acetals and hemiacetals. And that leaves me 4 minutes to cover reduction of aldehydes and ketones. Awesome. Actually, we can just about do it. Good. Any questions before we do that? Well, basically, there's 2 reducing agents that you need to know about. One of them is lithium aluminum hydride, and the other is sodium borohydride, NaBH4. And at first glance, these 2 reagents look very similar. They are, because aluminum's right below boron in the periodic table. So structurally, they're very similar reagents. But these are both reducing agents. And they are both sources of the hydride ion, H-. And that's a strange bird. You don't run into that one very often. So again, this is completely different from H+. This is H-. This is the hydride ion. It's got a minus charge and has a lone pair on it. So that's a very strong reducing agent. And happily, it does not matter which of these you use on any aldehyde or ketone. So we'll look at the generalized version first. Sodium borohydride is generally used in solution, usually in an aqueous alcohol solvent. So it's pretty common to have water and methanol or water and ethanol. That's the most common way of setting up this reaction. And by the way, water and methanol both react with sodium borohydride, but not as quickly as the carbonyl compound reacts. So as long as you add a good enough excess, you will get the corresponding alcohol. This will be either a secondary alcohol if we started with a ketone, or a primary alcohol if we started with an aldehyde. And then the hydrogen here, that comes from the sodium borohydride. The hydrogen in the OH will come from the solvent, the water and the methanol. But this H here comes from the hydride ion. And you're not responsible for the mechanism, but that is where it comes from. Or for aldehydes and ketones, these two reagents are interchangeable. It's just the reaction looks a little different for lithium aluminum hydride. Lithium aluminum hydride is considerably more reactive, and you can't use water or an alcohol or indeed any protic solvent, or it will react violently, and you might even get a fire. And one thing I have great difficulty convincing students of is that fires are bad. Fires are bad. They're a bad thing. So instead, we usually use diethyl ether or some other solvent like that. Can I just write ET2O? I think we've already defined ET, not extraterrestrial, as the ethyl group, CH3CH2. And you can write it that way too if you want. So we're going to use an aprotic solvent here, because fire bad. And only after that do we add water or dilute aqueous acid. And we do that extremely carefully so that we don't get a big fire. And you'll get the same thing. You'll get, are they still going fire good? Yeah. So you'll get the same type of alcohol. Secondary alcohol if we start from a ketone, primary alcohol if we start from an aldehyde. And we'll do at least one example. So for aldehydes and ketones, these two reagents are interchangeable. It doesn't matter which you use. They will both result in the reduction product. So for example, if we started with our old friend, and I really only have time for this for now, I think. We started with our old friend acetophenone. You can flip a coin and use either one of those reagents. In real life, if I had a choice, I would try sodium borohydride first, because the general rule is use the smallest hammer you can get away with. And if the stupidly reactive stuff works no better than the less reactive stuff, let's go with the less reactive stuff and maybe not try burning the building down. So that's what I would do. And I would expect to get benzyl alcohol. So this is just CH2. Oops, I lied. Not benzyl alcohol. Phenethyl alcohol. Not that I care that you know what it's called. That's what you'd get. So the hydrogen comes from the hydride ion. I would expect lithium aluminum hydride would give the same result. The reason you need to learn about both reagents is twofold. First of all, in real life, it's commonplace that you will try something and it won't work. So it's nice to have an alternate reagent. If I tried this and it didn't work, then I'd go to the lithium aluminum hydride. The second reason you need to know about this is we'll revisit these reagents when we get to chapter 10 on carboxylic acids and esters, and there we will find these two reagents are not interchangeable. Now, then it will matter which one we use. But other than that, actually, I'm out of time, so I think I'd better leave it there, and we'll get this up onto YouTube, and I guess I'll see you guys on Wednesday. Does product in second last reaction has H2O group? No, this is separate, like that. Sorry about that. This OH is attached here, that H is attached to the other one. Very good, see you all on Wednesday.